Hello, Melvin. Tell me where we are today.
So today we are in the Colutron laboratory of the University of Melbourne. And this laboratory is essentially an ion beam implanter facility. And what we are doing here is we are implanting atoms into substrates like silicon and diamond.
Okay, what can you use that for?
So we are mainly focusing, of course, on preparing something like quantum devices, qubit devices, that based on donors, especially, or dopant atoms in silicon.
Yeah. So what's specifically good about the Colutron?
So one neat feature about the Colutron is that it allows us a really precise control over single atom implantation. Right. So we can really implant exactly one atom, not just two or so, and we can also fairly precisely locate the position where we want it, and it allows us to create ordered high precision or high fidelity arrays of donors or atoms that are very shallowly implanted into silicon, so very close to the surface where we need them in order to be able to control them.
Yeah. How do you stop them going too far? Is it all about the energy?
It's all about the energy, yeah. Right. So it's just it's not MeV, so we are not talking about mega electron volts. Yeah. This episode could be called kilo electron volts if you want so, and we are sticking with energies below typically 20 keV in order for the species we are interested in, like phosphorus and antimony, and that allows us to implant them typically around 12. Anywhere, let's say, between 7 and 20 nanometers deep, with an average of about 12 nanometers. But you can end up with plus minus 2 or 3 nanometers placement in precision in the depth, which is acceptable, at least. It seems like the quantum computing community has advanced their protocols and architectures far enough to be able, let's say, accommodating this error. And that's the main reason why ion implantation gets more and more interesting, because it's a standard semiconductor tool, of course. And if you can use that to create such arrays that are not, let's say, atomically precise, perfect, but on the other hand, large scale, of course, then you have essentially a win-win situation.
So you're kind of using each individual atom as a quantum processor,
basically as a qubit, as a unit or building block of a large quantum processor architecture. And what you want to do is, of course, eventually entangling them all into a large superimposed state to eventually unleash the performance of a quantum computer, right? And for that you need to have them placed in an ordered array. You can't just have them randomly, because each of those donors is essentially equipped with a sulfate gate to tweak and modify them. And then with all these gates involved, you can then tweak their interaction accordingly to coherently couple them all together.
Right, okay. So we're embedding something into the silicon, and then you need to be able to somehow telephone in some data and then telephone the data back out again.
Basically,
that's what the gate is?
That's what the gate does, essentially, yes.
So you need to not only implant, but you need to also have a connection.
So the fabrication process is, of course, very complicated, and here in this lab we just overtake one part of it, which is essentially the precision placement of single atoms in silicon. And then those chips go to our colleagues or our collaborators at the UNSW, where they implement all the nano surface electronic circuitry that is then used to essentially control, manipulate those donor spins. So the entire process flow is, I think, composed of over 70 steps.
70?
Yeah, more than 70, and to get just one device.
Right, okay. But once you've got, one really good device, then you can solve every problem in the universe, is that right?
We are not that far yet, no. So we are just doing everything on a small scale, of course, so proof of principle devices. So what we've shown already is that we can, as I said, that we can reliably implant single atoms in silicon chips, not just any atoms, but those that are, of course, really necessary to build let's say, a donor qubit device, as we say.
So what are the kind of things you're implanting with that?
So we are mainly implanting phosphorus and antimony. We can do bismuth as well, but the first two are the main, let's say, donor species of interest.
And they're all in the periodic table, one to the right of silicon.
Yes, right. So they are group 5 elements, have one electron more. That makes them very useful, of course, for the electronic readout.
Right. So the silicons all connect, they're 4 bonds to each other, and the phosphorus in there will connect one and have one left over that you use as the qubit. Right, okay. And so you're just sort of smashing that in there, are you?
Yeah, so as ion implantation states it, we are essentially applying brute force, shooting the ion in, or the atom in form of an ion that creates a lot of damage, of course, in the lattice, and then we have to anneal those silicon, or in other cases diamond crystals as well, which is done thermally in order to re-establish the crystal, or the single crystalline structure.
Right. Yeah. So annealing, you just heat it up.
Essentially, yeah.
And all the bonds mend themselves.
Yeah, it's basically mending itself, the material. And then at the same time, you basically anneal also the donor or the dopant atom onto a substitutional lattice site so that it sits perfectly instead of a silicon atom on the side where you have it.
Right, okay.
And then it's also, as we say, electrically activated.
Yeah.
And I think the main feature here is that we can reliably implant single atoms that have a very low energy. Because we harness the signal they induce when they get implanted into the substrate, and this signal tells us whether the implant has basically occurred or not.
How do you mean signal?
It's an electric signal, so our samples or our chips are equipped with surface electrodes. Essentially, they operate like a PIPS detector or solid state detector, the samples, so when you implant an ion or an atom into the substrate, it creates electron hole pairs because it stops. It not only creates damage in the lattice, but also electron hole pairs, like light does in a solar cell, right? It's a similar principle. And we can detect those electron hole pairs. So we sweep them to the electrodes, and that gives us one distinct signal pulse, right? And by combining this, for example, with an atomic force microscope cantilever, or generally a scanning stage, we can then do this with spatial resolution and create arrays of single atoms and silicon.
So the fact that it's an atomic force microscope, is that important, or is it just the mechanical control that you have?
This is just the mechanical control.
So this is a kind of typical physicist bodge, to take something good over here and then stick it in here and use it for something completely different.
Right, in the end, yes, yeah.
Okay, how did you come up with that idea?
Oh, well, it's pretty straightforward for a physicist to think about it. I mean.
And is it just UNSW you work for, or you get other people coming as well?
No, we are mainly predominantly collaborating with UNSW on this project. We have some internal projects with Diamond, so creating deterministic arrays of color centers in Diamond.
And that's still a qubit, ultimately?
I think they are very interesting for quantum sensing applications, scalable fabrication of quantum sensors for all sorts of purposes.
So talking about scalability, how much can you scale this? Can you go up to quite big arrays, or is it just little ones so far?
The biggest arrays we've implanted here was about 50 times 50 single donors, and that is plenty given what we have fabricated so far in terms of qubit devices. So at the moment we are operating in the single qubit regime, right, with at least silicon donor qubits. So I think we have enough meat here to create, let's say, deterministic qubit devices that are composed of 2 donor qubits or even 4.
And that's the target, is to get
that's
to
about
4
the target,
qubits.
So it's in the end, it's a proof of principle setup. And
so that's an array of over 2,000, right? But you only use a couple of those.
Yes, essentially, you basically just pick the best you want, somewhere in between, and then you essentially smash on the surface circuitry on those and hope for the best.
Right, okay. When we're talking single atom, I mean, that's kind of mind-blowing, right? Because you have a sample of antimony up here, which might be, say 1 gram.
5?
5 grams?
Yeah, about.
Yeah, so 5 grams of antimony is 100 trillion or something, maybe 10 trillion atoms.
I believe you.
And you managed, I'm sort of roughly, Avogadro's number, right? Okay. And then you managed to persuade just one of them to go down there and go into the thing, and none of the others?
Yes, so of course you have a continuous beam, so you get many ions per second going through the apertures, but you can select them, of course, with ion optical lens systems, so electrostatically. And then at the very end of the beam line, you have only a couple of ions per second, that would hit the target,
Yeah.
and that can be dealt with very fast beam blankers, and of course our detection setups, and as soon as one ion goes through out of, let's say, a couple per second, the beam blanker is so fast that it can blank out the others.
Really? Right.
Yeah, the response time
So
is
it's just like, go, stop.
yeah, it's 50 nanoseconds, and compared to that, the average time pitch between ions that have a rate of 5 ions per second is much longer, and so you suppress accidental double implants by 0 point, I don't know.
And was that developed here, that fast blanker? Or
The fast blanker was developed here as well.
Yeah.
It's a nice feature, but it's not a particularly hard tool to develop.
Yeah. But it sounds like you've done a
It's
whole
a
lot of quite good things, but put them all together
Yeah, we have to
one
put
really good
together
system.
a lot of stuff, of course, and our technical stuff helped a lot. And has to be basically combined with a smart algorithm. And it's fairly standard for mega electron volt ions because they are easy to detect, because they deposit a lot of energy in the substrate. But when it comes down to KeV ions, which is very interesting, of course, for the shallow implantation, then the signal diminishes very quickly. And for that, you need very advanced detector electronics. I think the most exciting, let's say, ultimate result that I would like to be part of is, of course, realizing a deterministic donor qubit device. May it be a single or two. Would be nice if one such device would come out of this laboratory. That is something I'm, let's say, striving for already since 2015.
Right.
Meanwhile, and I hope we are pretty close now to realize this. Maybe I don't want to lean too far out of the window, but maybe by mid this year we might have one such device available, or several actually.
Okay.
That's I think that's very strive worthy.
Okay.
Yeah, to achieve.
Well, good luck.
Yeah. Thanks a lot.
Thank you.
Thank you.